And for the remaining of today, we're just going to do a few more things about the priors. And so if you remember what we did for the example, we are using what we called weakly informative prior, right? Like I put for beta 0 and beta 1, I was given mean 0 and then a large standard deviation, right? Just to, because I don't know much about it, I would just let the data decide how they're going to determine like the inference for the intercept and the slope. But there are other things you can do. And so I want to cover two ways that are also interesting. If you do have more information coming in, then you might want to give a more informative prior. And two ways you can do this. One way we call it subjective prior, or like informative prior in some sense, and the other one is conditional means. So let me first talk about the subjective prior, meaning that I already have some information. I want to incorporate that into my prior specifications. Okay. So the first step that we all need to do when you're trying to do subjective prior is to standardize the data. And the reason is that without standardization, the parameters beta 0 and beta 1, they are very hard to interpret. Okay. But if you standardize, which means we put things on a similar scale, and you can see that, like say for both x and y, we do this. So yi star, which is the standardized outcome, will be, you just standardize it to be, I think, yeah, standardize it that you are doing minus the mean from each observation divided by the standard deviation. And you do that for both. And in R, you can use the scale command to do the standardization. And what I did is I just created a new variable with std, stands for standardized, at the end. So I have two more columns now in my data that I have the standardized log total expenditure and the log total income. Okay. And let me show you that when you do standardization, when you plot them, the shape doesn't change at all. And I'm just like standardizing for the variables one by one. And the relationship, as you can see here, wouldn't change. The scale definitely changes. I mean, the range of the x-axis and the y-axis, but the general relationship doesn't change. But doing standardization helps us a lot in terms of interpreting what beta 0 and beta 1 is. So, for example, so first of all, when you standardize a data or like a variable, the standardized value that you have, which is the xi star and the yi star that we have, is representing the number of standard deviations that the observation falls below or above the mean. Okay, so let me just ask you, what would in our context, what does it mean if you have an xi star to be -2, and what does it mean to have yi star to be +1? I'll pause here so you can talk to your neighbors. So what do you think in the context? Well, so xi itself is the log total income, and then yi itself is the log expenditure, but now we standardize them. So what do they mean? What does it mean when you have xi star, which is the standardized log income, to be -2 in the context? Okay, let me ask the question before that. What does xi star equals to 0 mean? I see you nodding. So, Patrick?
Mean, yeah. It's the mean of the x, all the x. Its value is equal to the mean of the sample size.
Right. So when you have 0 values for those standardized values, it's just like it's the mean, right? So if xi star equals to 0, that is to say that for that CUI, consumer unit I, their log income, they make the average log income. Okay. But then if you start to have non-zero values next to 2, meaning that you're making 2 standard deviations lower than the average income, right? And then similarly, for the response variable, which is this yi star, once you standardize it, when it equals to 0, that's the average log expenditure. And if it's +1, it's this CUI is spending 1 standard deviation above the average. Okay. But then, of course, the standard deviation itself, I mean, it's from the data, so to be more exact, you have to interpret those as well. At least I think, as you can see that when you standardize it, xi star and yi stars, first of all, they have different meanings. But more helpful, in fact, sorry about a lot of words here, but more helpful here is after you standardize, I'm putting equation 21 and 22 here just to re-express the model. I'm still using the same parameters, okay, beta 0, beta 1. This is a little bit of use of notation, but you know what I mean. I'm just working with the standardized outcome and the standardized predictor values now. So the intercept now is expected standardized log mu I star for a CU that has the average log income, right? That's what we're talking about when you have xi star equals to 0, then that's beta 0 in terms of mu I star, and that is telling us the expected standardized log expenditure for that CU. The slope, I mean, again, will still reflect the change in the expected standardized mu I star when, yeah, let me just finish reading. Standardized log income increases by 1 unit. And or now you standardize it, you can say that it's when the log income variable increases by 1 standard deviation, okay? But I would say even more helpful is now the slope, once you do standardization, equals to correlation between the xi star and the yi star. Okay. This again, so correlation is measuring the linear relationship between two numerical or continuous variables. Okay, and once you do standardization, beta 1 itself actually equals to the correlation. Okay. So when you get this, well, you might start to realize, okay, if I have some strong opinion about their correlation, I can express them now in terms of beta 1. And that's why this is helpful. When you do standardization, okay, and then try to incorporate that information into it. And then for correlation itself, which is beta 1 here, so of course if you have positive correlation, I mean, which going to be like expressed in terms of positive beta 1 or negative beta 1 if you have negative. And the absolute value of the correlation indicates the strength of their linear relationship. Okay, and we know that correlation goes from -1 to +1. Okay, that's just how it is defined. Close to 0, meaning that it's very weak linear relationship. The bigger that goes to 1, the stronger of the positive correlation. And then the smaller it approaches to -1, the stronger of the negative correlation. Okay, so that's what it is. Okay, so standardization helps a lot in terms of, I think, making things interpretable. And then in particular, for the two parameters, the intercept beta 0 and the slope beta 1, I think the meanings are much more obvious. And then, well, if you have strong opinion about once you standardize how the, say, like the average log income, for example, that what would you think the expected standardized log expenditure will be? You can express that into your prior distribution for beta 0. And then for the slope as well, if I have very strong opinion about the correlation between the two variables, then I can express that in terms of the prior distribution of beta 1. So let me just give you a demo. So for the subjective prior, we're gonna again just start easy, simple. We assume independence across all of the parameters. So we did this before for our weakly informative prior. And for the intercept beta 0, if one believes a CU of average log income will also have an average log expenditure, then we can use a normal prior for beta 0 center as 0. Okay, because that's just like average goes to average. Okay, and the standard deviation in the prior, which will reflect how confident you think of this relationship. I mean, like average goes to average. Say now, for example, in fact, normal 0, 1 is, I think, pretty strong in that case because we already standardized the data. Okay, so for example, you can give normal 0, 1 as the prior for beta 0 once you standardize the data. Okay, for beta 1, because beta 1 is the intercept. Beta 1 is the slope as well as it represents the correlation. So we can also use the normal here generically. you can use equation 25, which is normal, like say center at mu1 and standard deviation S1. I'm giving an example here that, say, in the expression of 25, we know that, equation 25, that we know that mu1 is representing the best guess of your correlation, right? If I think it's 0.7, I'm going to give mu1 to be 0.7, just as an example, okay? And if I sort of like have okay, like belief or okay, strong enough belief about it, I can put a small-ish standard deviation like here, okay? If you do not have like too strong an opinion, you're just going to give a bigger standard deviation in that prior distribution. So, for example, you can give 0.7 as your best guess of the correlation, and then with the sureness of standard deviation 0.15. So this will be how you can specify a subjective prior, okay? But that needs to be done on the standardized data, okay? Because otherwise things do not make too much sense. But like again, I showed earlier that once you do the standardization, the relationship, I mean the plots, the shape doesn't change at all. So the things that you find out from the standardized data will still be very relevant to what you could have done with your original scale. It's just the original scale working, trying to give a subjective prior is not easy to do. All right, so, and of course for sigma, well, sigma again, I think always hard to give an informative prior, so we can always just stick to the default of a weakly informative gamma 1,1 for the precision. And this is the whole setup of the prior that I talked through about. And then now if you go to R, nothing changed much, actually. You just have to, I mean, the model actually didn't change for the JAGS script because we're still specifying the same stuff that we're doing, right? But what's going to change is we're going to start to give different data. Y, instead of the original scale, we're going to give to the standardized Y, right? And X going to be the standardized X. So I think the writing the model part doesn't change, the model string doesn't change, but it changes here. So you see that my Y now becomes the standardized log total expenditure with the STD at the end. And X is the standardized log total income. And then, of course, I have to change a little bit of the list of the data just to reflect my prior that I expressed earlier. Okay, so for sigma, we give 1 over sigma squared to be gamma 1,1. So our A is still 1, B is still 1. That's fine. And then that mu 0 and G0, that's the prior for beta 0 when we standardize it. And I said we're going to give a normal 0, 1, right? So that's what it is. And this mu 1 equals to 0.7. Remember, that's my best guess for my correlation. So I put that as the mean. That G1 to be 44.4, that's because, again, JAGS takes the precision in the D norm, so you have to be careful. I think we gave standard deviation to be 0.15, so we just do the math, 1 over the square root of that, which gives you 44.4. Okay? So then everything is straightforward. You can start to run it. Now you can see that the beta 0, which I mean, 0 is included in the credible interval now, and that will be something interesting to notice. And also, I want to point to your attention that remember, when we're doing the weekly informative prior, we didn't even, remember when we first run it, it was super sticky for beta 0 and beta 1, right? And then we start to do more thinning and stuff. So standardization overall is also helpful just to, I mean, get rid of the correlation overall, so it's going to help with the mixing. So this is just the first round that I did, and we didn't do any extra thinning and stuff, so it mixed pretty well in terms of the MC-MC diagnostics. So for example, I only included beta 1 here, just as a demo, okay? But that will be, I think so, right? Wrong. I guess this is the wrong plot because I think I used the posterior underscore new. But anyway, beta 1 is fine. Yeah, I think anyway. But from the output, we know that it should be fine. I will update this afterwards. All right, so this is how you can do a subjective prior. It works on the standardized data. Okay, so think it through, and then you can play with the code and then get a more sense about how it is done. and think it through. What does it mean when you have your beta 0 and beta 1 in the model when you're working with the standardized data? Okay, I think that's very important. And in fact, if you do have prior information that is useful to go into your regression model, then you standardize the data and then introduce them in terms of this subjective prior. Okay. All right, so the last one, I'm gonna cover this really quick. And another one prior that you are able to give is what we call a conditional means prior. So the way that you can think about this is, so again, this case is working on the original scale of the data, okay? But we know that the original scale in terms of the interpretation might not be the easiest if you think about beta 0 and beta 1 directly. So one way to get around that is, what if we state prior beliefs about some expected response value conditional a particular choice of your x? Okay, so for example, I know some, say for example, I will show you in a slide in a minute, but say for a CU of log income 10, for example, and I think the mean of that mu I for that CU should follow a particular distribution. Okay, so if I give it my mu I, given my xi, I have some idea about what the mean should follow. Maybe it's in terms of a normal distribution. Then you can specify that. And what we need, because we're doing simple linear regression, we only have two unknowns, beta 0 and beta 1. So if you try to, so pretty much we're trying to avoid giving prior to beta 0 and beta 1 directly, because we don't know what they mean on the original scale. Okay? But what we're trying to get around with it is, instead of giving prior to beta 0 and beta 1 directly, we're going to try to give prior for some mu, like say mu1 and mu2. If we know they're x1 and x2, we want to give prior to the mean of those observations. Okay, so instead of working with beta 0 and beta 1, we're going to work with some mu1 and mu2. And the thing is, because you only have two unknowns, right? And you have two conditional means here, you have two unknowns, two equations you can solve for the other two. I mean, say I don't know beta 0 and beta 1, but if I have mu1, mu2, and x1, x2, I know those values, I can express my beta 0 and beta 1 by solving it, and then that can translate into a prior specification. Okay? So again, we're going to assume independence for all of the parameters, and then we focus on this linear relationship in equation 33, which we have seen many times. So for example, we're going to try to use this linear relationship to give prior information. So for one predictor value, let's say x1 equals to 10, that's log income of $10 of that CU. I think the mean, which is mu1, which is beta 0 plus beta 1 times 10, is going to follow a normal distribution with mean 8 and 2. Let's just say. I mean, again, everything is working on the log scale, so it's a little bit not intuitive. But I was trying to play with the numbers on the original scale and then just put those two down here. So this is one way, right? I have one conditional mean, meaning that I specify my mu1 if I know what my x1 is. And that's my prior belief. Okay? So as you can see, I'm not giving prior to beta 0 and beta 1. I'm giving prior to mu1, which I know has this linear relationship. Okay? Similarly, if I get a different predictor value x2, say 15, then I think, okay, so typo, there must be I think x2 equals to 12, sorry. And then I think, okay, the mean mu2 of that should be a normal centered at 11 and standard deviation 2. So this will be, okay, instead of giving priors to beta 0 and beta 1, I'm giving priors for mu1 and mu2, and then I can solve it. Okay? So solving it is this. And this is pure algebra. You all can do this. So we have two unknowns, beta 0 and beta 1, right? And then we have two equations. Mu1 equals to beta 0 plus beta 1 times x1. And mu2 equals to beta 0 plus beta 1 times x2. So we can express our beta 0 and beta 1 in terms of mu1, mu2, x1, x2. Okay? And essentially what we're going to do is we fix the values of x1 and x2, like I showed you earlier, right? And then we have prior distribution for mu1 and mu2. So we're able to give prior essentially to beta 0 and beta 1 through mu1 and mu2. So in terms of, the prior from mu1 and mu2, this is what we give in equations 40 and 41. In terms of JAGS, it's pretty fun. So you see that the model sampling part is still the same, right? But in the priors, as you can see, we're not giving prior to beta 1 and beta 0 directly, right? We're giving prior in terms of mu1 and mu2. Okay? So that's why mu1 is tilde d norm, and mu2 is tilde d norm, and beta 0 and beta 1 are expressed. So now in terms of distribution, it's deterministic. So it's assigning to the two solved equations that we came up with. Okay? And then for sigma, let's just use gamma 1, 1, because it's always hard to deal with that standard deviation. Okay, sorry, I think I went over 1 minute, but we did start a little bit late, so hopefully it's not too much. And yeah, so that's what I prepared for this. And then I did put a lab on our Moodle site, but I guess we don't have time to do it now. And what I would do is I will change the due date for that because we didn't get to do at all today. And so no class on Thursday, and on Tuesday when we come back, it's going to be the take-home midterm. So the in-class midterm. Okay. And I will try to make some office hours next Monday in case you want to come in. But I do have office hours today and tomorrow if you have questions. Okay. All right.